Dear students, welcome back to Akadimos Online. We all know tautomerism is a type of structural isomerism where two or more interconvertible isomers, actually the tautomers, exist in dynamic equilibrium, primarily differing in position of proton and the arrangement of bonds. This process often involves functional groups like carbonyls, hydroxyls, or the amino groups. Our guest teacher Nurul Haq says tautomerism is a spontaneous equilibrium phenomena. Let's concentrate how he elaborates tautomerism now.
Dear students, in today's class I am going to discuss an important part of organic chemistry, tautomerism. Actually, tautomers are functional isomers, or you can say structural isomers. But here, not simple structural isomer. It is a spontaneous equilibrium phenomena. Remember, it is a spontaneous equilibrium phenomena. Actually, in our syllabus, majorly we have keto-enol tautomerism. Keto-enol tautomerism. I have discussed in hyperconjugation discussion. If you have not followed that, please go to the hyperconjugation part of the video. There you will get idea. Actually, here also alpha hydrogen of aldehyde or ketone, mainly alpha hydrogen of aldehyde or ketone will show the tautomerism phenomena. It has reality, not like hyperconjugation hypothetical. It has direct evidence. This is alpha. You know, like hyperconjugation, this alpha hydrogen sigma CH donate to pi antibonding of C double bond O. Now you will get minus charge on oxygen. And that minus is enough stable to go H plus from this end to this end. And you will get a new structure which is really exist and give reversible sign. You will get CH2 double bond C OH CH3. This is called keto form. You know C double bond O, that is called keto form. Keto form. And this is called enol form. Enol means double bonded carbon, you know, in, and all OH with in, that is enol. And these two forms, their structure are different. These are structural isomers. You can say these are functional isomers since they have their functional group C double bond O. Here the functional group is alcohol OH. But this is not like other isomers. I told you, this one keto form and two enol form remain in equilibrium. Here I have taken acetone. Remember, never you will get 100% acetone in acetone. Whatever the percentage, there you will get enol form. It may be 0.01%, but you will get enol form in reality. And since you know, when a phenomena is reversible, that is interconvertible, then thermodynamics or thermodynamic stability will tell you which one has major contribution, which one has minor contribution. Here, generally, you know, keto form more stable than enol form. See the difference in the structure. Here you get C double bond O, here C double bond C. Now, C double bond O much more higher in energy than C double bond C. If I am not wrong, then C double bond C energy near about 600 kilojoule per mole, whereas C double bond O bond energy near about more than 700 kilojoule per mole. That's why this keto form generally more stable than enol. That's why its contribution more, its contribution less, but never zero. You will get some contribution of enol form. And they are in equilibrium. Any equilibrium phenomena always thermodynamically controlled. Stability will tell you which one major and minor. Now, what is the application? Now, There are 3 alpha hydrogen, all 6 alpha hydrogen may participate in tautomerism, and which will increases the carbon-carbon bond order, decreases carbon-carbon bond length, and increases carbon-oxygen bond length, increases carbon-oxygen bond length. If I take this structure, then this carbon-oxygen bond length should perfectly C double bond O, but in actual, that carbon-oxygen bond length greater than C double bond O due to this tautomeric enol form, where you will get carbon-oxygen bond order 1 and in keto form carbon-oxygen bond order 2. This contribution decreases the bond order of carbon-oxygen, increases the bond length between carbon and oxygen. More alpha hydrogen, more high tautomers, more increase of carbon-oxygen bond length, more decrease of CC bond length. Remember. Now, another thing, if I take this structural isomer or enol form, the hydrogen which are directly attached with alpha carbon, due to electronegativity difference, they are acidic. But you know this hydrogen is more acidic than this. That means enol form will increases the acidic strength of the alpha hydrogen. Since in the enol, you will get hydrogen with oxygen. And remember, it is not hypothetical, it has reality. Now, I am going to give example of different keto-enol tautomerism. And later, another system also show tautomerism that I will show you. But first, I will show the major part of our syllabus, that is keto-enol tautomerism. I am going to give example. I am taking when you will get 2 different hydrogen. See the example. Butane 2-on. See here, you will get alpha hydrogen. This is alpha hydrogen. And this alpha hydrogen is secondary. This alpha hydrogen is secondary, 2 degree. Here alpha hydrogen, this is primary. This is 1 degree, this is 2 degree. And you know from general organic chemistry, 2 degree hydrogen less acidic than 1 degree hydrogen due to Plaza effect of the methyl group. This is less acidic. Less acidic. This is more acidic. Now, here you will get 2 different enol forms since these 2 alpha hydrogens are different. If I take this hydrogen, participate in tautomerism or to get enol form, then the enol is this one. If this hydrogen participate, you will get this enol. See, these 2 enols are different. Their IUPAC nomenclature different. Here it is 2-ol. Here it is 2-ol, but the double bond here at the 2 position. Here double bond at the position 1. Now my question is, enol contribution less due to carbon oxygen pi bond energy more than CC pi bond. But my question is this, among these 2 enol, which one major? If it is 0.1% present, among 0.1%, which one more, which one minor, or both are equally? See the problem. I told you, it is an equilibrium phenomena. That means interconversion permissible. And if interconversion permissible, then always major, minor, you will get by considering their thermodynamic stability. More stable, major. If interconversion permissible, that is called thermodynamically controlled. Now, if I do compare the stability among these 2 enol, see, here you will get 6 hyperconjugation alkene, and here you will get 2 hyperconjugation. Now tell me, which one more stable? These are alkene. 6 hyperconjugation always increases stability. Since hyperconjugation is nothing but additional bond. Additional bond means additional stability. This one more stable than this. Since it is interconvertible reversible phenomena, this enol you will get major. which is thermodynamically controlled enol, major. This is minor, kinetically controlled. Now question will arise, why it is kinetically controlled? Thermodynamically controlled you got, since it is more stable, that's why thermodynamically controlled, thermodynamic stability more, and major since it is reversible. Now it is kinetically controlled enol. How it is kinetically controlled? You know, when alpha hydrogen participate to form the keto-enol tautomerism or to form the enol, it will show its acidic character. See, and this hydrogen also will show its acidic character. Now tell me, which one more acidic? This one more acidic? That means if this hydrogen participate to form enol, which is more faster, since it is more acidic, and this hydrogen is slower, that means kinetically fast will form this. This enol rate of formation more, this enol rate of formation is less, but since it is interconvertible, it can easily backs to the ketone, then goes to the this, then ultimately thermodynamically stable major, since it is reversible and interconvertible. Remember, when there are different enol, always do compare their contribution by taking their stability only. Keto-enol tautomerism solely thermodynamically controlled, and it is a reversible phenomenon. I am going to give another example. Take a cyclic ketone. This is cyclic ketone. Similar, only I have changed here, it is a cyclic. Now, here also you will get two different alpha carbon. This is tertiary, this is secondary. And here you will get two different enol. Two different enol. I am drawing the two different enol. This is one enol. This tertiary hydrogen participate, and this is another enol. It is thermodynamically more stable. See, here 3, 2, 2, 7 number of hyperconjugative interaction you will get here, and here 2, 1, only 3 hyperconjugation. Which one more stable? This one. That's why this one major. This one major, and this one minor. So always we will do compare which one major, minor by considering their stability. Hyperconjugation will compare the stability of alkene. Now I am taking another example. Just I am changing the example. Like previous, but I will put a pi bond. It was the previous example. I am taking here a pi bond. See, I am taking here a pi bond. What I have changed? Only I have taken a pi bond. Now, here also you will get two different enol. This one and this one. This is pi bond. This is pi bond. Just change. See the magic. Here already there was a pi bond. You got a new pi bond in enol, which is isolated. No conjugative relation, no resonance, since consecutive to single bond is there. Isolated pi bond. But here see, conjugated pi bond. You will get resonance here. And you know, resonance is more predominating effect than hyperconjugation. Now, previously it was minor. Now it becomes major due to conjugate double bond. There you will get resonance between these two double bond. And this is isolated double bond minor. Stability, not only by hyperconjugation, also there you have to consider different factors. But the key point is stability will control the contribution. Now, I will take another example. Let this one, keto. Here also you will get two different hydrogen. Two hydrogens are different. But remember, if I take this hydrogen, then there you have to put pi bond here. That is consecutive pi bond. Consecutive pi bond means this carbon becomes sp hybridized. Angle should 180. But here angle, you can form this ring if angle is 120. So 180 by force you are doing 120. There are 60-degree angle strength. And due to angle strength, never you can form consecutive pi bond in small ring. Remember it, rebate in your mind, consecutive pi bond in small ring never form, never exist. That's why this hydrogen never participate in tautomerism. Only this hydrogen participate in tautomerism, and you will get this one. See the structure. Surprisingly, what do you got? It is a very common, highly stable phenol, carbonic acid. The ring is aromatic. In the keto form, it was non-aromatic. It is aromatic. Now see, surprisingly, enol here highly stable, 99% enol, 1% keto, more or less, suppose. I don't know the exact data, but it is very close to 99% contribution, enol. In the beginning, what I told you, keto generally more stable. But here, say, enol more stable due to highly stable aromatic ring. You know, aromatic compounds are highly stable due to extensive conjugation of the pi bond in the ring. Now, see another example. Here you got the aromaticity as a special factor which will increase the stability of enol. See this example, highly important example. This is an alpha hydrogen. From the beginning, what I have discussed, only alpha hydrogen participate in hyperconjugation. But see, if this alpha hydrogen participate in hyperconjugation, there you will get consecutive double bond in ring. That is highly unstable due to angle strength. That's why these two alpha hydrogen never participate in tautomerism. That means it will not participate in tautomerism. It will not give any enol. No. You know this is alpha. And the conjugate of alpha is, this is beta gamma. Here gamma hydrogen will participate in tautomerism. Interestingly, this gamma will participate in tautomerism. How? This gamma, this is conjugate, and H will go with oxygen. But what structure you will get? See. Here pi bond, here existing pi bond, it becomes phenol. See this example. And here also, since it is aromatic phenol highly stable, you will get near about 99% contribution. It is 1%. And here gamma conjugate hydrogen participate in tautomerism. That means alpha hydrogen normally participate in tautomerism. Gamma can also participate in tautomerism if it is conjugate with the alpha due to this pi bond. A very interesting example. And the enol is aromatic, that's why its contribution is 99%. Now, if I take this example, another, I told you, this never alpha hydrogen here participate in tautomerism. Why? Consecutive double bond in ring never form. But gamma may participate. Since gamma is conjugate with this alpha. But remember, here in gamma position, no hydrogen present. No hydrogen at gamma. This hydrogen never participate in tautomerism. That's why it will not participate in tautomerism. Never you will get any enol form of this benzoquinone structure. This is called benzoquinone, and anything color due to this benzoquinoid structure. I have given an example. Since alpha hydrogen not participate, there are no gamma hydrogen, it will not participate in tautomerism, it will not give any enol. Another example, different, see, this one, oxygen. This hydrogen never participates due to consecutive double bond, but this hydrogen may participate. If I take this alpha hydrogen, you will get a structure. See the structure, that is 2 double bond in 4-membered ring. This is OH. Can you tell me what is this? It is an anti-aromatic structure. It is an anti-aromatic structure. Anti-aromatics are highly unstable. No one go to anti-aromatic state like anti-bonding state. Highly unstable tautomerism will not occur here. No tautomerism you will get here due to anti-aromatic structure. In the previous example, there was no alpha hydrogen, no gamma hydrogen, no tautomerism. Here due to enol is anti-aromatic, that's why no tautomerism. See my example, highly important. Especially for JEE advanced aspirants, focus on this example. Alpha hydrogen here not participate in tautomerism. I will take gamma hydrogen which is attached with nitrogen. And you know nitrogen, if hydrogen attached with nitrogen, its acidic strength increases, no problem. Draw the tautomeric form. If I draw the tautomeric form which is reversible or interconvertible, then you will get a pyridine derivative. You will get a pyridine derivative structure. See, it is aromatic. Aromatic pyridine structure. It is non-aromatic. Normally, what do you think? Aromatic highly stable. If I do consider isolated molecular stability, its contribution maximum, its contribution less. But here surprisingly we will get in JEEMAINS when you will take in vapor phase. Vapor phase being intermolecular attraction is near about 0. Isolated molecular stability is considerable part, important. If I do consider isolated molecular stability, then aromatic will play an important role, and this form is more stable in gas phase or vapor phase. If the vapor phase, this form is, enol form is more stable, major. But when in liquid phase, due to effective hydrogen bond in liquid phase, although it is non-aromatic, but its contribution is more and major. Remember this. In liquid phase, this one major, and in vapor phase, this one major. This is extraordinary, an exceptional example. I have given so many examples of keto-enol tautomerism. There are so many examples remaining in field. If time permit, I will discuss in next part of video. Stay with us. I will discuss more example on tautomerism. Thank you.